So this is going to be around a topic that's become very kind of trendy in machine learning in the last couple of years, I would say, automatic model selection or auto ML, where we're going to try to take a lot of the work out of tuning your machine learning models. So this is machine learning for machine learning. There's lots of algorithms and parameters out there, right? We've gone over a lot of use cases, different algorithms you can use, even for supervised learning. There are a lot of options algorithms wise, and all of those algorithms have parameters, right? So for logistic regression, you can choose how you're going to do regularization. For deep nets, you can choose how many layers you have. For ensembles of trees, you can decide how many random splits you want to use, how big of a subset you want to use for each tree, how many trees you want to do. So there's lots of algorithms out there, lots of parameters, but really we're just trying to learn the one thing, right? The one function that maps best the inputs to the outputs. And we don't even have time to try close to everything, right? Especially when we include maybe different ways of pre-processing the data, all the different algorithm parameters you can futz with, all the different data transformations you can do. We don't have time to try even close to everything. So wouldn't it be great if we had a way to kind of predict how well a machine learning was going to do based on the data that you saw before you could, hey, that sounds like a machine learning problem, right? So can we use machine learning to kind of drive the bus here of actually doing the model tuning for us? And if you're if you're asking yourself this question, you're in pretty good company. I feel like every single grad student in machine learning, they get a few classes under their belt, they start talking about model selection, and they're like, hey, why don't we just use machine learning to do machine learning? It's a common intuition, and it's not wrong. There's lots of a good idea. Most of that idea is really good. The only problem with it, as we're going to see as we kind of step through this talk, is it doesn't get you as far as you would like. And that's coming from somebody who really believes in these techniques, who really thinks they're super useful, these AutoML techniques, who's done a lot of development on them for BigML themselves, who's gone to a lot of workshops. I'm a firm believer in the usefulness of all these techniques. They just sometimes overpromise. And so we're going to talk about what that overpromising means and where the work is left for you as a practitioner, as a data scientist, even when we have AutoML. So Bayesian parameter optimization, really common way of doing this sort of solving this AutoML problem. So the performance of an ML algorithm with some set of parameters is data dependent, right? You get some data in, and then you can measure performance. And so we're just going to learn from our previous attempts, basically. We'll train a model, and then we'll evaluate it. And then after we've evaluated a number of models or different parameters or whatever, we'll learn kind of a simple regression model that predicts the performance of future models, right, based on this data that you've given us. So you learn 10 or 20 models on the data, then we train a model that maps the parameters of those models that we've learned to the performance of those models. And then we can say, hey, here's this model we haven't tried yet, but based on the ones we have tried, its performance is going to be fantastic or not so good, or we're not sure. And that's what we're trying to do. We're trying to use this machine learning model to estimate the quality of future models that we haven't trained yet. And then we can use this classifier to search through the space of possible models and say, hey, here's a promising one to try. Here's something that will probably work better than what we've tried so far. And so here's a little diagram of that process. We have these, on the left, you see a bunch of parameters, a bunch of models that we're going to evaluate. We're considering the type of model to actually be a parameter. And so we have this box, model and evaluate, that will split the training and test data maybe a bunch of times. It will look at a set of these parameters, and then it will spit out some kind of number. So here's this first set of parameters. It turns out to be a set of parameters for a deep net, and according to the evaluation process, it gives us a score of 0.75. All right, so let's try another one. Here's the second set of parameters. We do modeling and evaluation there. It's a logistic regression. It gives us 0.56 for our performance. So no better, right? It was, the performance was worse on that one. Next, hey, we try ensembles, and look, we get a value of 0.92 for performance, so that's really good. Now we have a data set, right? We have these parameters and we have them mapped to numbers, and we want to predict the numbers from the parameters. And so we can just do machine learning here. Our inputs are the parameters to the algorithm. Our output is the performance that we measured. And then we can use that model to kind of reorder the queue here of parameters that we're evaluating. So this is saying, hey, I think parameters number 6 is more promising than parameters number 4. Let's bump that up in the queue. Let's evaluate that and see how we do. And you can do this over and over again. Every 8 or 10 or 15 models that you learn a new model that predicts performance of these parameters, and then you reorder your queue. You find new models to evaluate based on the results of that training. So there's a little bit of cleverness here mathematically, right? You don't want to pick the thing that's predicted to be the best performer on your next iteration. Like if this model said, hey, I think parameters number 6 is going to perform the best out of any of these, that's not quite what you want, because the best thing is something you've already tried. What you want is something that's close to the best thing, but also has a little bit of uncertainty around the estimate. And so your model has to have a way of measuring that uncertainty. In practice, we use Gaussian process or approximation of Gaussian process models to generate something that will tell you not only what you expect the average performance to be, but how much uncertainty you have around the estimate. And so you want to pick something where, yes, it's probably going to perform well, but also there's a little bit of uncertainty as to how well. And so, you know, that uncertainty is what might give you a result that's better than what you've already tried. So you want to kind of balance between high quality and also novelty, something that you haven't tried exactly that yet. But again, this is kind of a mathematical detail. Like basically you're learning a machine learning model to predict the performance of these models that you're trying on your data. So it's a very simple idea. It seems like magic, right? Here's this guy with the cards and the smoke. It's a magician, and so now all my problems are solved, right? I don't have to do anything. I can just plow my data. Once I've done all the data cleaning, I can just plow it into this process and magically get a good model out. No, unfortunately, no, that's wrong. So please don't think that. First of all, you're selecting a model based on held out data. So this means you have to have enough data to do an accurate model selection. If you've got tens of thousands, hundreds of thousands, millions of points, then this isn't something you have to worry about as much, right? You've got enough data to do the model selection and train the model and have a holdout, you know, a separate holdout. You've got enough data where you can keep splitting it and still get a good model. If you've got like hundreds of points or even just a few thousand points, sometimes you don't have enough to do model selection in this way. Every time you want to do any kind of model selection, be it AutoML or just training a regular model, which is itself a process of model selection, you need data to drive that process. And so the more models you want to select from, like if you want to do AutoML, which trains a whole bunch of different models rather than just, you know, one or two, then you've got to have enough data that when you run the test, it'll be able to accurately tell you the difference in performance between those models. If you don't, then there's no reason to use AutoML techniques. And second, there's still issues here, and those are what I'm going to try to clear up for the rest of this talk. So the first issue is metric choice. Remember from before, we need to pay really close attention to how we measure the quality of a model. If we use accuracy and the data is really unbalanced, that's a big problem, right? Geez, I feel like we've seen that before. Where have we? Yes. Here's where we saw that before in the evaluations talk just minutes ago. We talked about how accuracy can be a bad metric. So this is an important choice. You need a metric. You need to measure that performance number for each model in a way that corresponds with the way you're going to value the model as a practitioner. And so here's just a little flowchart. Now we don't have to be as careful about this as we do when we're actually evaluating the model. When we choose a metric, what we're choosing is a metric to drive the search, right? You want models that are trying to increase this thing. But the way we finally evaluate the model, we could do it in some other way, some more precise way. Here, you just want to pick a metric that's good enough, basically, to drive the search in the proper direction. And so there's a little, I developed this little flowchart a while ago that just gives you a general idea about how to pick a metric for your problem. So the first question you ask yourself is, are you going to mess with that probability slider, right? Or are you just going to use 0.5 as your threshold and not screw around with it? If you are, then you can use one of the metrics where you're that depend on your being able to slide that threshold around. If you're not, you can just use accuracy if it's a balanced data set, or you can use one of the other kind of balance sensitive metrics for an unbalanced data set. And then the other question, one of the other questions I'm asking here, this flowchart is available on our blog as well. But one of the other main questions I'm asking here is, do you have a ranking problem? And what that means is, do you really have a problem where the top n instances are more important or are regarded to be more positive than the next n instances, for example? So this is the case that Tom was talking about, where you have medical diagnosis, for example, versus stock picking. In medical diagnosis, the AUC is a good idea because we just have to label the people positive or negative, and we don't get points for the most sick person being the most positive label, having the highest probability threshold. It's just that we want to pick a threshold that labels as many people sick as many of the sick people sick as possible, and as many people who are well as well possible. This isn't a ranking problem. Within those groups, it doesn't matter where you fall in the ranking. You just want to make sure that you label everyone correctly. Stock picking is a bit different, right? In stock picking, you do care about, like, let's say you can only take positions in 20 stocks. Well, there's 5,000 stocks out there. So if you're able to say, you know, here's the stocks that are the most likely to give me price increases over the next, you know, whatever period you're trying to invest in. Here's the 20 stock. Here's the stocks you should buy. Here's a ranked list. The ones at the bottom will probably go down. The ones at the top will probably go up. All you care about is how good you do on the top 20 in that ranking, right? Because you're only going to be able to buy 20 of them. If you miss some really good performers, it doesn't really matter as long as you get some really good performers in that top 20. So this is a place where precision at 20 or precision at 50 is a better metric. And so these are the problems that I consider to be ranking problems, where the ranking of the data is kind of more important than the absolute prediction. So that's a little guideline to choosing your metric, and now you have to choose a holdout. So should you use cross-validation? Cross-validation is a good tool some of the time. Many other times it's disastrously bad when you have information leakage. BigML in their AutoML suite offers the option to pick a specific holdout set, and should you use it? Again, this sounds awfully familiar. This sounds something, oh, that's right. This sounds like what we were talking about earlier when you hold out data where there might be information leakage. You don't want to hold out data that where some of the points in your test set have information, or some of the points in your training set have information about some of the points in your test set. And remember, here's this other example where we had users where their photos had information about each other. Again, you're in this situation where you could have problems based on the fact that you've held out data that has information about the test data that you're using. So BigML, again, if I go back here, BigML offers you the option to use a specific holdout set, right? So instead of just saying, evaluate these model candidates by using cross-validation, you can say, evaluate these model candidates on this specific holdout set. And that way you can select your holdout set. It'll be valid for your problem. You'll have a holdout set that's properly separated from the training data, and the search will be driven in the proper direction. Again, that's the goal here, is to give the search a way of evaluating these models that is informative to it, so it actually finds you the best model. So you're trying to tailor the search for your problem as much as you can. Yeah, again, these situations are common when you can't use cross-validation. The situations are common when the data comes in some kind of groups, either groups of days or groups of users or groups of locations. And the solution is to hold out whole groups in your holdout set. Just like I said before, it's possible that this isn't a problem in your data set. But again, if you even have the slightest suspicion, you should try both. You should do an optimal with both settings. And again, if you get much worse results when you hold out specific users or specific chunks of time or specific groups, then you're in one of these situations where you have to do that all the time. If it seems to make no difference, if you get consistent results from doing specific holdouts or not, then you're fine, and it's not something you have to worry about specifically. The remaining issue here, one last issue we have here is model choice. Model choice, that's crazy, right? Like we just talked about AutoML as a way to automatically choose models. Why do I have to pay attention to model choice even now? It's because, again, there's little way of this AutoML process. There's not a great way for the AutoML process to know which model is the best for your particular situation. So performance of the model in terms of accuracy or precision at whatever, however you choose to model performance, that's not the only issue here. There's other issues that can often come up. One is retraining. Let's say you have some kind of a process that monitors the model, either accuracy or the performance characteristics of the model as it's performing, or maybe it's looking for concept drift with an anomaly detector or some other process like that. Let's say you plan on retraining the model once in a while. Will you have the same amount of data to retrain the model, or will the amount of data be dramatically different? Like maybe you have 10,000 points from the last year, but really in the future, when you have to retrain, you might only have a month of data, or you might have way more data. You might have your data might be increasing exponentially as you accumulate customers or something like that. And so you might have more data in the future. So that's going to inform your choice a little bit, right? Maybe you're on the edge of being able to use one of the more complex modeling techniques right now, but in the future you'll be able to use that with no problem. And so maybe it's a good choice to kind of build your infrastructure around one of those more complex techniques now. Fit stability. How confident do you have to be that the model's behavior is invariant to small changes? One example from my own life is I had this model that was performing in the markets, and it was a tree-based model, and so it would give the traders a score every time, essentially every time it wanted to trade, every time it thought it was a good idea to buy or sell, it would give our traders on the floor some kind of number, some kind of score. And of course, this is a tree-based model, so when certain indicators would cross a threshold in the trees, would jump to one side, from one side of a split to the other in the trees, then the score would just absolutely go nuts. It would change dramatically, right? There'd be these huge discontinuities in the score, even when the indicator variables, the input variables, were moving very little. So for example, I went from volume of 5,000 to volume of 5,001, and all of a sudden I got this massive increase in probability. That doesn't make any sense to the trader, right? To the person who's consuming the model's predictions. And so that, like, it sounds like kind of a mundane concern, right? To not alarm the person who's consuming your model's predictions, but in actuality, that's the kind of thing you have to worry about when you're actually deploying a machine learning model. Like, that's part of the process of evaluation is this person who's consuming the model's predictions going to be satisfied with them? And that's part of that equation. And so if you don't want to have these massive discontinuities, you have to use a model type, you have to train a model type that doesn't have these discontinuities. So AutoML can help you with that by saying, you know, here's a deep neural network. It performs about as well as an ensemble, and it won't have these discontinuities. So that could be a driving factor of, for picking a deep neural network, for example, instead of choosing ensembles, even if the performance of the ensemble is marginally better. And then the other thing, prediction speed, it's something people don't worry about until it becomes a big problem. So there are cases, again, that I've experienced personally, where I say, okay, here's a deep neural network. It'll give you the prediction back in, you know, a millisecond or two, some amount of time that feels very small to these people. And they're like, oh, okay, a millisecond or two, surely that's, you know, that's fine. Until we need to do like 1 million predictions, and it takes them, you know, quite some time to do that, right? It starts to add up to minutes or hours. Even at very small prediction sizes. And people don't think about this. People don't think, oh, I have, you know, 100 things coming in each second, and I need the predictions of those within the second. Like, that starts to be a lot of compute work compute that needs to be done. And so, you know, the prediction time for deep neural networks, for example, we're talking about something that's orders of magnitude higher than the prediction speed most of the time for logistic regression. Again, like hundreds of times, thousands of times more expensive. And so if you've only got a tiny difference in performance between the two, you can solve a lot of your own problems just by using the simpler model that will be blazing fast and will never be a problem speed-wise for you if the performance is acceptable. And so I've already talked about this a little bit, right? I've already talked about the things that are different between models that have nothing to do with performance. So you have speed, you know, the risk of overfitting, the amount of data you need to fit it. These are all relevant. These are all still relevant even when you're using AutoML. And then finally, just to say this again in a different way, you'll start to get used to these ideas the more you look into you know, how we look at machine learning models in kind of the academic world and the mathematical world. You'll start to get used to these axes on which we think about machine learning models. But just to kind of reiterate again, to some of the trade-offs you can experience here: weak versus slow. Simple models are weaker, but they're really fast. Slow models are, you know, stronger, but they tend to go slower. Interpretability versus representability. The more complex the function you can represent, the more of a black box it starts to become, the harder it starts to become for a human to understand the predictions. You know, it's not impossible. There are techniques out there that let you understand these black box models on some level, but there is, you know, an aspect of model interpretability where you're just not going to understand it as well as you are something very simple. Confidence versus performance. With these simple models, in general, you get kind of high bias, low variance models. You can be sure that the fit, that you can be more sure that it's not overfit when you're using one of these simple models. With the complex models, you don't have that certainty unless you do like a lot of out of sample testing. There's a lot of opportunity for the model to do overfitting of various kinds. And then bias versus data hungry. In simple models, the model's bias, the parametric form of the linear models, for example, it obviates the need for tons of data to fit it. So again, with linear models, if you're trying to fit a line, you only need 2 points, right? That's high school, that's middle school algebra, middle school geometry. But if you are trying to fit something a lot more complex, then you need more data to fit it. And so a summary here. We can use some simple tricks and use machine learning to help us search through the space of possible models. This isn't anything magical, and even machine learning wise, it's not even that complex, although it's getting more complex every year as more papers are released. But still, the central idea is pretty basic, and the data that we're working with is usually small, right? We're usually talking about at most hundreds of models, and so it's pretty easy to learn, you know, to learn in whatever way you want over this small data. However, there's still, even when you have this, there's still lots of choices you have to make. There's still lots of ways you could screw up or, you know, really help out the search to give you the thing that you're looking for. And then finally, just to kind of belabor this point, because it is very important, automated model selection relies on data. It's not any different from learning a decision tree. Learning a single tree is also model selection. You're selecting the best tree out of all the trees that you could possibly learn. You're using the data to select it. This is similar. You're using the data to select the best model out of all the possible models. If you don't have enough data to do this selection and also train the underlying models that you could select from at the same time, then this is going to go poorly. So as you get down to small data sizes, where small data sizes could mean a few thousand points, you have to start to think about this. Can I actually trust these results? Look at the variance, you know, maybe do a few of these AutoML, do a few runs of AutoML and see what the variance in the results is like, and you know, see if you can really trust the results when you've got small data like that.